So I want to conclude today by just talking about free space loss and link budget. They're not as often used as the frisk transmission formula, but they are a little bit helpful. Free space loss, often abbreviated FSL, is how much power an EM wave is going to lose when traveling between two line-of-sight points in free space. And what we see is that free space loss is going to be 4 pi times the distance between the 2 points, or the distance that it travels, divided by lambda, and we just square that. And so that becomes, if we do a substitution in for lambda, which is just c over f, that flips the f into the numerator, we get 4 pi df over c. And hopefully what you're seeing here is that we're not actually attenuating the wave due to power losses. It's just that it's getting more spread out. It's covering a bigger surface area the further away we get, right? The sphere of radiation is a bigger surface area the larger d is. And so that's what accounts for this free space loss as power transmits, because it's radiating out as a spherical shape here. And what this formula is showing us is that there are basically two things working against us the further away we get, the bigger the distance between a transmitter and a receiver. And that is that this is increasing with the square of both the distance that they are separated, and then also with the frequency. So free space loss increases with the square of the frequency and with the square of the distance there. So often what is said is that free space loss follows what's called an inverse square law, which is often said as it takes 4 times the power to go 2 times the distance. So if I want my signal to travel due to free space loss, if I want my signal to travel twice as far, I need to crank my power up by 4x. Most often you're going to encounter free space loss specified in dB, and so this calculation right here translated into dB is just going to be 20 log the distance plus 20 log the frequency minus 147.55 dB. So pretty simple calculation for power transmission due to free space loss. The last thing I want to introduce is what's called link budget, and this is a method that's used to account for all losses in a communication system. So here we have a typical communication system, which consists of your transmitter, your transmitting antenna, all the cables and connections that connect your transmitter to your transmitting antenna, so this path here. We then account for free space loss. We then have a receiving antenna, and then the receiving antenna's got to connect to the receiver through some sort of cable and connections. So the total received power by the receiver is going to have 3 components. It's going to be the losses due to the transmitter. We're going to have the losses due to the free space transmission here, and we're going to have the losses inherent in the receiver here. And all of this is going to be in dBm, so we're just adding all these up together since they're decibel measurements. So the received power is going to be the transmitted power that in dBm that goes into the receiver. I've got the antenna gain in dBi, and then I've got whatever my other losses are due to cables, connectors, reflections, etc., LT. I then have my free space loss, which we just talked about. We've got other free space losses due to fading, obstacles, mismatch, stuff like that. So this is going to be, if that EM wave is for some reason absorbed by a conductor or something like that, it's going to do some attenuation. And then we've got the gain of the receiving antenna, and then other losses is due to the cables, connectors, mismatch, and stuff like that. And so that method of calculating for all the power is called link budget.